everyone. My name is Sri Lakshmi and I'm here to explain the concept of binary search trees. Before knowing the binary search tree, you must be aware of what's meant by a binary tree. Generally, a binary tree is a nonlinear data structure in a hierarchical manner. It will having maximum of two children and it should not exceed two children. That means every node must have a two children. So binary search tree is nothing but it's an advanced method or implemented form of a binary trees. In the binary trees, we are not able to search an element appropriately. So that's why we took binary search tree. It gives an optimistic time complexity in searching. So binary search tree is a rooted binary tree data structure. That means a nonlinear data structure where each internal node has a key and the keys in the left subtree are less than the keys of the node, while the keys in the right subtree are greater. In other words, left child will having the lesser values and the right child will having the greater values. The basic operations of this BST is nothing but searching, insertion and deletions. The properties, the most important property is nothing but order of login. That means the time complexity of the binary search tree. The reason of inventing binary search tree is for searching technique. And other two are left subtree nodes must have the lesser values than the root node and the right subtree should have greater values than the root node. So the definition of insertion is nothing but to insert an element maintaining the properties of BST. It should not violate the properties of BST while inserting. And in BST, it can also have zero children, one children, or two children, but it should not exceed other than the two children. Insertion refers to the process of adding a new node with a specific value into the tree while maintaining the BST properties. While inserting, we have two kinds. While inserting in the empty node and while inserting to the existing tree. So while inserting a node into an empty tree, we have to be careful that the node which we were inserting is nothing but a root node. And while inserting into an existing tree, we should focus on the conditions of binary search tree. That means the properties of binary search tree. Is the insertion which we were doing is definitely satisfying that property or not? So let us see. Here an empty tree and I'm inserting 2, so 2 becomes the root node. And if I want to insert a 4 node valued node, I have to check with the 2 that is 4 is greater than 2 or less than 2. Obviously 4 is greater than 2. So greater values are always assigned to the right part of the tree. So 4 went to the right part of the 2. In the similar way, 1 is less than 2. That's why 1 is assigned to left part of the 2. We have to traverse the whole tree to add an element. That means, suppose see if I want to add a 5, I have to traverse the node 2. I have to check whether that 5 is greater than 2 or less than 2. It's greater than 2, so I'm going to the right part. And I have to check with the 4 also that 5 is greater than 4 or less than 4. It's obviously greater than 4. So that's why I'm going to the right side of the 4 and I'm adding the 5 there. For similar way for the tree 2. So here 2 is greater, so sorry, 2 is less than 3, that means 3 is greater. So I'm going to the right part of the 2 and 4 is greater than 3, that means 3 is lesser. Lesser means I have to add to the left part of the node. So node which is the node which is greater than the node which we want to insert is 4. So fourth left part is assigned with the 3. That means we are traversing. Traversing is nothing but the way we travel. Now, algorithm for insertion is if the root is null, that means there is no tree, the empty tree. Then we have to return the node which we want to insert. That will be the root of the node. That's it. Otherwise, if the root is not none, that means there already a tree exists. Then definitely we have to check that the value is less than or greater than. If the value is less than the root's value, then the value is assigned to the left part of the root node. This is nothing but a recursive function which is called recursively by the same function until the condition gets satisfied. This will work. If the condition is not satisfied, the recursive function stop recursing and it will assign the last value. It will assign the last recurring value. Next, if the value is greater than the root value, We'll go to the right subtree and assign to the right part of the root node. Now, while coming to the Python implementation of the insertion, we are creating a class called tree node. We are defining an init function, nothing but a constructor of Python. These are attributes where we are assigning values. So this key value is nothing but the key which we are giving as a parameter. Left part of the key and right part of the key is assigned to the none value. We are writing an insert function to insert an element. If the root is none, that means if the tree is empty, we have to create a new node. This is the line where we are creating a new node by calling this one. By calling this class, as I said, it's a constructor. The constructor can be, that means the instance can be called by the class name. So here we have passed the key value. It is going here and making a node. Here the left part is none, right part is none, and the key value is assigned to the key what we have done. So here we are creating a new node when if the tree is empty. And we are returning the same node because there is no nodes and the inserting node will be the root node. That's why we are returning only the one node. Otherwise, if the root is not none, then we have to check whether it is less or whether it is 5. If it is less, then we are going to the left part of the node, left part of the root node, and we are inserting there the left one. That means not the left one. We are checking here the root left is the insert root left is the recurring function call. Root left is going to here and root is replaced with root left. Again root left enters here. If the root left is none, no. That means it will check here. If it is also not satisfied, it will goes to the else part. That means root left also has to be compared and we have to insert whether we have to insert or not. If the root left doesn't exist, and then what it will do? It will just return the root. Okay, these are the recursive function. That means it is going to traverse root left. If I assign here root left, again if I come here and if I again say root left and the left part of the left root, left part of the root left part. I think you are wearing. I'll just show. If I take a right one, I didn't have a big tree here. If I take this one, I'm saying that if I came here and if the right part of the root exists, then again still go to the right part by checking the condition only. If it's greater only, we have to go. And if I check it's greater, then go to the right part like that. And this right part is came from this right of root. This is a recursive method. If it is correct, then the value can be assigned to the left part. The key is assigned here. And if it's not satisfying, it will go here and assign to the right one. Until this condition satisfies, until this recursion stops, the value is not assigned to these values, variables. And last, we are returning the root. So for that, we have assigned the left part and right part of the tree. Now we have to print them. Here I'm printing the tree in an in-order manner so that all the elements comes in the sorted manner. In-order traversal, pre-order traversal, post-order traversal are the three types of traversals. In-order gives a sorted array. So here, in-order traversal again is a recursive function. I'm calling root left. That means this root is replaced with root left after entering here if the root exists only. If I replace with root left, again it will check for the root left. If it is exist, again will be replaced. Like that I'm going to the last at most left part. In such a way I'm printing the root value and again I'm going to the right part. It's a order of the in order traversal. It's a rule of in order traversal. Again, if I check for root right, if it has happened, okay, I came to the last left node. And again, if I printed the root also, and if I have printed that one in order printed, I have printed the left one also, and I have printed root. And now I'll go to the right part of that root. Again, right. That means at most right, like that. It is nothing but entering into the main function if condition satisfied. We are assigning root value to the none. That means the starting value. That means now the tree is empty. So the first value where we insert will definitely be the root node. See here I have given keys and the first node is 50. Now definitely 50 will be the root node. As I said, for the empty node, the first node which we want to insert will be the root node. And these are all other elements which we have want to insert. And the next one is I'm accessing all the elements presented in the list by the variable called key. I'm giving this key value, this root value into the insert function and I'm inserting the key value. Now next I'm printing the in order traversal format. The output will be in this way. So that the inserting element first will be the 50 and then we'll get 30, 50, then 20, 30, 50. In such way, as I'm adding, the number of elements are increasing. If you see here, as I said, the left part of the root node will definitely having the lesser values and the right will having the higher values than the root node. Why I printed in order itself, to it will be easy to understand that if I took a 50 as a root node, not if it's definitely a root node. See, all the elements to the left is smaller and the right is larger. Completed the insertion part. Now the tree representation of this insertion part will be in this way. So first we are inserting 30, 50, then we are inserting 30 and all the elements to the left are smaller, all the elements to the right are larger. If we come to the time complexity for the best case insertion is order of log n and average case is also an order of log n. But the worst case is order of n. That means we have to go to n height. That means n levels. We must go to the n levels because it's a skewed tree. Skewed tree is nothing but it will be in the form of a linked list, only having a single children. And next, in the time complexity, in the best case, we'll having a balanced tree where height increases with the proportional to the log n. That's why we are getting log n as a time complexity. In the average case also, it's a partially balanced, so we are getting the log n itself. Now while coming to the deletions in the BST, we must focus on the three types of cases. First, deletion means what? Deleting a node from a tree. In this, there are three cases. So what's the three cases? First case is the deleting the leaf node. Second case would be deleting the node which is having a single child. Third case is the deleting the node which is having both the children. Now let us coming to the leaf node. Leaf node doesn't have any specific conditions to delete as it's a 60, 60, 30, 10 are here the leaf nodes. That means the node which doesn't have any children, zero children. So if I want to delete the 60th node, there will be no conditions. I can directly free up this node from the memory. That's it, that's enough. While I'm coming to the one child node, that means if I want to delete a one child consisting node, that means if I want to delete a 50. Now if I want to delete 50, while deleting this node 60, it's easy to delete because we can replace 50 with the 60 and free up this 60 place node. This is for single child. And for two child, we have to check the in order successor. We can check both the cases which are in order successor. First one is in order successor. We have to check the leftmost node or the minimum node of right subtree and the maximum node of left subtree. We can check the minimum node of right subtree or maximum node of left subtree. And we have to replace that node with the deleting node which we want to delete. That is for two children. If you see here, 20 is replaced with 30 and the 30th position, this node is freed up. Coming to the algorithm, if the root is null, that means we have to return null. No element is exists in the tree, we have to return that nothing is to delete. While coming to the third point, they were saying that if the deleted element, if the element which we have to delete is less than the root's value, then just we have to go to the left part. That means every small values than the root value exists in the left part itself. That means this is the step, these 4 and 5 steps are for traversing. If the element to delete is small, we have to go to the left part. If the element is greater, we have to go to the right part. Here we have to call recursively. That means the function is called recursively to have this transition. If the value to be deleted is equal to the root node, or the root's data. Now we are in the current node. If the node which we want to delete is equal to the current node where we were, then we have to check the conditions that is it having a two children, one children, or it doesn't have any children. If it doesn't have any children or having one children, we just replace that or we should delete directly. And next, if it is having the two children, as I said, we have to take the minimum value of right subtree or the maximum value of left subtree. Mostly, majority of the cases, in order successor is used. That means find the minimum value of right subtree. That means the leftmost node in the right subtree. So while taking the right subtree of the root node, and we were going to have the leftmost number of right subtree. We are going to the left node. We are still going to the left of left node. Like that we are going to the utmost left node. Then next we have to recursively call the delete function. We have to replace the element with that one, with the element which we want to delete. And we have to free up this node space. Minimum node space. We have to delete that one. We have to return. And next Python implementation of the deletion is we have first created class node as insertion, and next init function is this is the constructor attributes we are assigning the same as insertion. Now we are inserting the elements because we have to delete after the insertion itself. After inserting, this is the code for insertion. This is the code for insertion, and this is the code for printing that inserted values. After printing the insertion values, we have take another new function called minimum value node. Why we took the minimum value node? Because when the node having the two children, we must replace with the minimum value of the right subtree to the deleting node. That's why we took this function. Now here the current node, the temporary current variable is assigned with the node value. And if the current, that means the node's left part is none. If it is none, we should return the current value. If it is not none, we have to go to the left of left. That means we have to go to the left part of left node. And still we have to go to the left part. In such a way, we have to go to the left part until we get the smallest element in the whole right subtree. We cannot know that it would be the smallest one, but we can find that until the left one is ended. That means until the left current dot left condition satisfies, we have to roam here only. If it doesn't satisfy, we have to just return the current now where we are, in the which node we are. And the next one is deleting node function. Deleting node function, first we will enter into here. If the root node is none, we already know that return root. And if not, if the root value, that means the key is less than the root value, we have to go to the left subtree. As you already said, we have to enter into the left one, and we are giving the parameter as root dot left. That means here root is replaced with root dot left, and again we are checking root dot left is none or not. If not none, again we are checking is that less than the root left node. We are checking for every node. Every node in the BST has to satisfy the BST property. And the next one is if this is not satisfied, then definitely this or this has to be satisfied. That means key has to be greater than root value or equal to the root value. These are the recursive functions where we were traversing, and at last again we have to come here only. After traversing to every node, we must have a value for this one, and after recursively traversing here, we must have a value for right one. After that, again we are coming here. Again we were calling by the value which we have given in the root place. Again we are coming here. Definitely we have to come to the else part, so that we'll have to know that we came to the correct position to the element where we have to delete. That means the key value and the element value, that means the key value and the root value is same here. If that exists, then we have to check the conditions that whether it have a one child, zero child, or a two child. If it is having one child or a zero child, just we have to remove and replace the node. For that we are doing that. If the root left is none, if the left part of the root is none, we have to return the right part. If the right part is none, we have to return the left part. That is for child. If the node having the two children, then we have to replace with a minimum node. So for minimum node, we have already written a code we have to just call that node and assign with a temporary variable. We just want to keep that value in a temporary variable. Now this temporary node having the value which where we have to assign for the root value. Now we are taking a root value. This is the final value. We are replacing. This step is for replacing. Copying the in order successor value. We are replacing this root value. This the temp for the from the temporary value. We are keeping this minimum value of root tree, right subtree value to the root value, and we are returning the root itself. Completed. And here we are deleting the in order successor. I have already said that after replacement we have to free up the space, we have to free the node, and that this recursive function calls that deleting the step. At last we have to return the node root. This is the driver code where we are inserting all the elements, and then we are printing the we are deleting the element and printing that element. Printing what elements? The existing elements, the remaining elements. So first we are printing the in order traversal, that means before deletion. And after deletion of 20, we are again calling the in order traversal and printing the remaining roots. And again deleting 30, which is having one child, which is having it doesn't have any child, that means it's a leaf node. We are having 30 is having one child, and we are removing one child and printing the remaining elements. Here we are deleting 50th element, which is a root node, and also the node which is having the two children. And again we are calling the in order traversal, we are printing the remaining elements. Let us see. This is the printing statement where I have written iteratively. That means for every iteration, for every deletion, I am printing the remaining elements. So these are the elements before deletion, and these are the elements after deleting the leaf node called 20. So no condition for this. And for after removing the 30, the remaining elements are 40, 50, 60, and 70, 80. After deleting 30, the root node, then 50 doesn't exist, and this 50 is replaced with in order successor called 60. Here if you see, all the left are smaller and all the right are larger than 50. We are removing 50 by replacing in order successor. We are removing the leaf node called 20 without any condition, we can directly remove. And 30, which is having a single node, this 30 is replaced with 40. And this print statement can also be altered by changing the snippet of code by in this way. That means I'm directly calling deleting nodes 3 at a time and printing the direct result. I'm not printing for every iteration. So the output would be simple steps before deleting and after deleting. See, there are no 20, 30 and 50 nodes here. If we see the tree representation, before deletion, we having this tree. And after deletion, first we are removing 20. So leaf node, we are directly removing. So there is no 20 here. And while removing 30, we are substituting 30 with the 40 valued element. So we are just removing 30 and keeping the 40 there. While removing the 50, which is the root node, we have to replace with the in order successor or the minimum element or the leftmost element on the right subtree. That means the right subtree is nothing but 70, 60 and 80. This is the right subtree, right? And the leftmost node is 60. So we are replacing this 60 here and we are deleting the 50 and removing the space for this node. That's it. Now, while coming to the time complexity, it is same as insertions. And the best case and average case having order of log n, and the worst case is having order of n. Thank you. And the further concepts of BST is continued by Stravia.
Shravya. Now we are going to discuss about height of binary search tree. In a tree data structure, this is the structure of tree. The number of edges from the leaf node to the particular node in the largest path is known as height of the node. Let's see in this tree data structure, will the highest, the longest path is 1, 2, 4, and let's consider 2 as a node and let's find its height. 2 has one edge, so and the height will be 1 for 2. In the tree, the height of the root node is called height of tree. In this tree, let's see 1 is the root node. So it has the height of the one node has height of 2 because it has two edges. One is over here and another is here. So the height of the entire tree will also be 2. And let's see the code. Let's break down this code now. This defines a node class to represent each node in binary tree. Each node has value points to the left and right childs, which are initialized as none. Here we initialized and defined self dot value as value and self dot left as none, self dot right as none, which means the self dot left means the left side of the node. The left side nodes in the tree are initialized with none. The right side nodes are initialized with none. Means it doesn't have any left or right. Now this is the height function. The height function calculates the height of the node. This is the if the node is none, means if tree has no childs and no nodes, there is no root node, then the child is empty. When we have empty node, the height of the empty tree will be -1. If we have one element, one node in the tree, and then the height of the tree will be 0. And this is the recursive case. The function recursive calculates the height of left and right subtree. Left height equal to height of node dot left, right height equal to height of node dot right, and the maximum of left and right plus 1 will be the height. Example, let's take the first node tree data structure we saw here now. Let's see this only. So we are initializing root node as 1 and root node dot left is 2 and root node dot right node is 3 and root node dot left node is 4. And we are gonna print the height of the tree is the height of root node. As we discussed, the height of the root will be the height of the tree. Print height of the node 2 is height of root dot left. The output will be like height of the tree is 2 and the height of the node 2 is 1. And now we are going to discuss about light level of binary search tree. In binary search tree, the levels of nodes is the number of parent nodes that corresponded to that node. It is also the number of ancestors that node has up to the top node. The root node, which is topmost node, has 0 level because it has no parents. If a node has children, they both have a level of 1. The level of a binary tree is the highest level node of the tree. The left of the node is the number of edges between the node and the right node plus 1. This is it's the way to group nodes, but they are distance from the root. Let's see the meaning of this with an example tree. This will be the root node. It doesn't have any parents, so the level of the root node will always be 0. and these are the leaf nodes. 3, 7, 15, 30 are the leaf nodes, and this will be a level, and this will be the other level. The level of this tree is 2, means like the level of 10 is 0 as we discussed, and the level of 5 is 1, and 20 is also 1, and 3 is 2, and 7 is also 2, 15 2, and 32. Other than this, everything in this tree, it does, if something is does not there in this tree and they're asking for its level, it will return -1. So let's see the code for this now. Here we define the class, the line self dot value as value, self dot left as none, self dot right as none. This line assigns the value passed during creation of the node of self dot value attributes. This stores the data of the node. This one stores the data of the node. Self dot left equal to none. This initialize the left child of the node to none, means the node has no left child when it is first created. Similarly to right. Now let's see the finding of a node. Here we gave root value level equals to 0 if the root is none. If nothing is there in the structure, then it will return -1. If root dot value equals to 1, sorry, the root dot value equals to value returns the level. If the value is greater than the root dot value, then it returns the find value. Here we do, if we gave the name as find value left, root dot left goes to the left side and takes the value and sees the level and add-ons 1. Similar else, it goes to the right side and it increments to 1. Let's see the example of the same. This one, root node will be 10, root dot left will be 5, root dot right will be 20, root of left node will be 3, root of left right means left side, the right one will be 7, and the right for in the root, for the root, the right of the right, and to that right we have the left, then will be the 50, and the others, if the root right has another right, that will be the 30. Here we are printing the values of each node. For example, let's take node 10, which is root node, and 5, and 7, and 15, and 30, and 100. The output will be for the root node, as we know, it will return 0. For which is in the here, hit its level is 1, and 7, which is over here, it will be 2, and 15, which is over here. This its level will be also 2, and the 30 its level will be also 2, and the 100 which is not there in this tree and which we did not mention over here. That will be -1, which means that doesn't exist in the tree. And the next part will be continued by Hasita. Thank you.
I am Hasita. Now I'm gonna say whether the given node is a leaf node or not. In a binary search tree, each node has at most two children, a left child and a right child. The left child contains values less than the parent node and the right child contains values greater than the parent node. There are some nodes which doesn't have any children, that is both left and right child are null. Those we can call them as leaf nodes. Leaf nodes are found at bottom edge of the tree. There are some methods to find whether the node is a leaf node or not in a binary search tree. Let us see those methods. First, we will consider recursive approach. In recursive approach, we will start at the root node and we will consider a current node. If the current node has no children, both left and right, then we can say it as a leaf node. If the current node has a left child, we recursively check the left subtree, and if the current node has a right child, we will recursively check the right subtree. Another method we can see it as iterative approach. In iterative approach, we will start at the root node and we will consider a current node while the current node has a left or right child. If the current node has a left child, we will move to the left child, and if the current node has a right child, we will move to the right child. And the final node we will be reach will be known as leaf node. We will use some traversal techniques to find whether the node is a leaf node or whether the leaf node or not. We will consider pre-ordered traversal. The first node encountered without any child, we can say it as a leaf node. In post-ordered traversal, the last node encountered without any child, we can call it as a leaf node. In level order traversal, the last node encountered before a new level starts will be known as leaf nodes. Let us consider an binary search tree example. In this example, we can see 50 is the main root and we will say it is at level 0. The levels will be set after constructing the whole tree. And here the children for 50 are 30 and 70. Then we can say it as at level 1. 30 and 70 has children 20, 40, 60, 80, and we can say these are at level 2. 20, 60, 80 has some children 15, 25, 35, 45, 55, 75. And the later that it doesn't have any children, so we can say it as leaf nodes. As I said, the 15, 25, 35, 45, 55, 75 are leaf nodes. Now we consider a program to find whether the node is a leaf node or not. We will declare a class named tree_node, and in this class we will initialize a function def underscore underscore init underscore underscore set dot values. Here set comma values are parameters, and for any tree we should store the value, and we can say it as self dot value is equals to value, and for every node it will have left or right child. So at first we will initialize the left and right child to null. It means self dot left is equals to null, self dot right is equals to null. To find leaf nodes, we will declare another function. Def find leaf find underscore leaf underscore nodes of root. If root is none, there will be no leaf node, so we will return none. If root is not none, we will create an empty list with name leaf nodes, leaf underscore nodes. And we will declare another function to recursively traverse through the tree. Here dfs of node. If node is not none, we will go into that node and we will see if the node dot left is none and if node dot right is none. We can append this node value to the leaf underscore nodes as we create an empty leaf with the name leaf underscore node. In the same way, we'll go to the node dot left, node dot right, and root. We will traverse the whole tree and we will return the leaf nodes. Here we will return leaf underscore nodes. To first of all, we will construct a bind search tree. To construct a bind search tree, we will use another function def build underscore BST of values. If we have given no values, we will return none. As we can say, the tree is empty, it doesn't have any root, it doesn't have any leaf nodes, or it doesn't have anything. And so we will return none. If we have given some values, the first value will be considered as no root. It means root is equals to tree node of values of 0. And here we consider the first value as root, and we will go through the other values, and for those values we will use a for loop. For value in values 1 is 2, from 1 it will go to the length of the nodes, length of the values we have given. And here we will first take node is equals to root. If true, if while true, if the value of the node is less than node dot value, it means here the value is, we have given some input, right? In input is less than node dot value, it means root dot value, we will go to the left subtree. If node dot left is none, we will take as node dot left is equals to the value here we have considered. This value will be in the place of node dot left, and we will use break. If node dot left is not none, we'll go to the node is equals to node dot left. And in the same way, if value is greater than node dot value, we will go to the right subtree. And if node dot right is none, we can say node dot right is equals to tree node of value, and we will use break. If node dot right is not none, we can say node is equals to node dot right, and we will recursively traverse the whole tree, and we will append the values, and we will construct the tree in this way. And finally, we will return the root. Here we will come out of the class, and we can say if underscore underscore name underscore underscore is equals to underscore underscore main underscore underscore, and here we will take input values, and have built the BST tree. BST, we will consider a variable root is equals to big underscore BST to construct the tree, and we want the leaf node values, right? So we will use a variable. We can consider the variable name as leaf underscore nodes is equals to, we have declared one function to append the values and to store the values. That function name we have considered as leaf underscore find underscore leaf underscore nodes of root, and we will print the leaf nodes. In the output here we have taken values is equals to input, enter the values for the binary search tree, and here we will print the values, the required node values. And here we have considered node leaf underscore nodes. We will print the leaf node values. First it will take the input values, and it will construct a tree. In the tree it will see where the leaf nodes are present, and it will append the values in the list, and we will print the appended values here. Leaf nodes colon 2 comma 4 comma 7, as we consider an empty list, the values will be stored in a list. Now let us see on the program. Find the min and max element of any node in the tree, that is in order precedor and in order successor of any node in tree. Here in order precedor, it means the immediately precedes the node that immediately precedes in it an in-order traversal of the tree. Here we can consider an element, and we will do when we do an in-order traversal. In in-order traversal, the value where the element is present, the before one we can call it as in-order predecessor, and we will use the algorithm for in-order predecessor is, if node has a left subtree, the in-order predecessor is the rightmost node in the left subtree. Otherwise, the in-order predecessor is the nearest ancestor, that is to the left of the node path. Here, let us we can take these values 5, 3, 8, 2, 4, 7, 9 when we do in order traversal. we can say the values will be 2, 3, 4, 5, 7, 8, 9, right? 2. Here let us consider the node which we want to find the min and max element of the node is 5. Then in order traversal, the 5, let us consider 5 as the root. And here we can see in order traversal, the left of the value we can say we can call it as a in order predecessor, and the rightmost of the value we can call it as a in order successor. Mm, in order successor, the in order successor of a node in a BST is the node that immediately follow its in order traversal of the tree. Here the in order successor of 5 is 7, and in order successor of 2 will be 3. In the same way, the every element which has in order predecessor and in order successor. The algorithm for in order successor is, if the node has a right subtree, the in order successor will be the leftmost node in the right subtree. Otherwise, the in order successor is the nearest transistor that is to the right of the node's path of the root. Here let us consider this example. Here 10 is the root and it has two children, 5 and 15. Here we want the in order predecessor of root 10, and we can say that in the left subtree the largest number or the leftmost, here what we say, predecessor is the rightmost node in the left subtree. So the rightmost in the left subtree, the rightmost node is 7. We can say that 7 is the in order predecessor of 10. And here we want the in order successor of 10. Here we can say in right subtree the leftmost value, and here we can see that the leftmost value is 12. So 10, the 12 will be the in order successor of 10. Here see, in order predecessor of node 7, in order predecessor, the rightmost node in the left subtree of 7 is 5, right? Left rightmost node. And in order successor of node 7, the leftmost node in the right subtree of 7 will be 12. This one. Actually, let us write a program for finding the min and max value of a node in the BST. Let us consider a class and class node, and we will initialize self.data to store the value, and we will take left and right children as none, and we will consider another function which means here we represent node as node class as each node of a binary tree. It has an initial. We will initial the function def underscore underscore init underscore underscore self dot data. Data will be the value of the node and the left and right subtrees of the node. Here we will initialize them to none. As we have to find the min and max element of the node, we'll consider parameters as node. Here the parameters for this function will be node. If node is none, return inf comma in float minus inf. It means if node is none, it returns the minimum element as float of inf and maximum element as float of minus inf. This is the standard way to handle empty subtrees in recursion, allowing other valid nodes to determine the actual min and max values. And here we will recursively call the left underscore minimum, left underscore maximum is equals to find underscore minimum underscore maximum of node dot left. First we will go to the node and we will return the values, and next we will go to the left subtree and we will find the left minimum and left maximum of those, and again we will go to the right subtree and we will find the left minimum and left max we will find the right minimum and right maximum of that node dot right, and we will calculate the min and max value as min underscore value is equals to minimum of node dot data comma, here we will want to find the left minimum value, so we will consider node dot data left underscore minimum and right underscore minimum. Here we've taken and we have used a min function, so it will return the minimum value between those, and for the maximum value we will use max underscore value is equals to max of node dot data comma left underscore max comma right underscore max, and it will return the max value. Here we have written those and we will return the minimum and maximum value. Now let us take some input. Here I want to take root value as 10 and root dot left is equals to node of 5, root dot right is equals to node of 20, and root dot left the left node of the 5 will be 2 and right node of the left will be 8. It means 5. Right, 8 will be the right node of 5, and in the right subtree the left node of 20 will be 15 and right node of 20 will be 25. Yeah, that's we have taken root value as 10. In left subtree we have taken the child of 10 will be 5 and the children for 5 are 2 and 18. In the right subtree the child of 10 will be 20 and the children of 20 are 15 and 25. We have written those, and we will take min underscore value max underscore value is equals to, here we have declared this function find underscore min underscore max of node. We will use that function and we will return these values, and we will use print statement minimum value in the subtree rooted at node 5 for this. The value minimum value will be printed and the maximum value for this tree will be printed. So here we have taken at node 5, right? So the minimum value in the subtree noted at node 5 is 2 and the maximum value of the subtree noted at rooted at node 5 is 8. Here we can write, let us write the in order traversal for this function. Will go to the left subtree, that is leftmost 2 and parent node 5, 8, 10, 15, 20 and 25. The in order traversal for the tree will be this, and we can say we have considered we want to find the minimum and maximum element of the node 5. So in this in order traversal node 5 is here. The leftmost of this node 5 is 2 and it will, we can say it as the minimum value, and the right value of node 5 is 8, so we can say it as a maximum value. The output will be printed. This will be the output. So the program for to find the minimum and maximum value of a node in the BST is this. We will initialize the self.data is equals to data, self.left is equals to none, self.right is equals to none. We will consider another function find underscore min underscore max to find the min and max element of the node, and we will take float inf will be the minimum value, float minus inf will be the maximum value. We will consider left underscore minimum, left underscore maximum, and we will declare the function here is equals to find underscore min underscore max of node dot left, and we will consider right underscore minimum right underscore maximum is equals to find underscore min underscore max of node dot right. We will consider the min value between node dot data left dot minimum right underscore minimum. We will consider the maximum value between node dot data left underscore maximum right underscore maximum. We will return those values, and we will take input some numbers, and we will construct the tree, and we will print the minimum value and maximum value by using print statements. So the output will of the given node is this. Thank you. Thank you.